My name is Matthew Egbert. I'm a senior lecturer at the University of Auckland, and I'm looking forward to taking the next 10 minutes or so to tell you about a new computational model that I've been developing. It's a computational model that's intended to simulate systems similar to the one that you can see in the upper right-hand corner of this slide. And what you're looking at there is a motile oil droplet. It's a droplet of oil that has a chemical reaction going on its surface that allows it to propel itself around in its environment. And as I'll discuss in a moment, the behaviors that these droplets perform are rather interesting for a variety of reasons. This droplet that you're looking at here is performing a kind of chemotaxis, where it's moving up a pH gradient. And very interestingly, higher pH conditions are good for the reaction that's causing the motion. So what arguably you can see in systems like this is a form of self-preservation or self-maintaining behavior. A behavior that's produced by a reaction that causes a droplet to move towards environments that are good for that very same reaction. And for this reason and others, this kind of system has been of quite a bit of interest and inspirational to several people within our artificial life community. And I've been interested in these systems for quite a while now. But I'm not a chemist, and it's hard for me to work in wet labs. And even for people that do have wet labs, to experiment with these systems and to come up with variations of them is an extremely difficult thing to do. And I thought it would be really interesting to have a computational model which allows me to change to an arbitrary degree what kind of chemistry is going on the surface of these droplets, and really to let me explore the space of possible chemical reaction-driven motility, if you will. So I'm going to present that model to you in the next few slides. So let's take a closer look at these motile oil droplets and how they move around. I've tried to create some schematic diagrams on the left here for describing that motion. The basic idea is pretty simple. There's a chemical reaction that's going on the surface, and the product of that chemical reaction decreases the local surface tension on the droplet. So if we imagine, just for a moment, that this droplet has this reaction going on everywhere at the surface, but it's happening a little bit more at the top. So the local surface tension at the top of the droplet is lower than everywhere else on the droplet. This causes something called the Marangoni effect to occur, which is essentially the flow of the surface material to equilibrate the surface tension. And this happens, it carries material from low surface tension areas to the high surface tension areas. And this causes a coherent flow around the surface of the droplet, which is what propels it forwards. So I've drawn in these black arrows here an example of this convective flow, which is caused by the asymmetrical surface tension that's indicated by the yellow star. Okay, so that's how the droplet moves. But how does it perform chemotaxis? Well, if we imagine for a moment that this droplet is situated in an environment where the left-hand side of the environment is more conducive to this reaction, so it allows the reaction to happen more quickly, as is the case when the pH is higher. So we imagine there's a higher pH on the left-hand side of the droplet than the right-hand side of the droplet. In this case, there's more of a difference in the surface tension. The surface tension is decreased farther on the left than it is on the right. And I hope that you can see that that would cause a reorientation of the convection flow, the convective flow, towards the region where more of the surfactant is being produced, where the surface tension is being lowered more. And again, what's really interesting about this is the kind of self-preserving nature of it. The flow orients towards whichever local area of the environment is facilitating the reaction to occur more quickly. In previous work, we've shown that this kind of behavior, what we've called metabolism-based behavior, can facilitate evolution in a wide variety of ways. I've written a few papers on that, and sadly I don't have time to cover those various evolutionary benefits of this kind of behavior. Because today I'm interested in something a bit different. I'm interested in how it might be possible to take this kind of basic form of behavior that's shown by these motile oil droplets, where they just move to whichever local environment is best for their motion-producing mechanism right now, and to try to investigate how we might have smarter motile oil droplets, droplets that behave in a slightly more sophisticated way, maybe droplets with some kind of memory, or droplets capable of learning something, and things like this. And that's the purpose of the model that I'm presenting today. I'll now run you quickly through the model. The model consists of an environment in which there can be one or more motile oil droplets. Each oil droplet has a fixed size, and for each oil droplet, we track the concentration of different chemicals at the surface of the oil droplet. So we don't think about the concentrations within the oil droplet. They're not captured in our simulation at all. All we think about is the amphiphilic molecules that are embedded in the surface at this stage anyway. And we can have 1, 2, 3, as many of those surface chemicals as we want to track in the model. And we track their dynamics. Their dynamics change by way of 4 processes. So the first of these is simple chemical reactions. So we can say that we have 2 different chemicals that are embedded in the surface of our droplets, A and B, and we can specify chemical reaction where A and B combine in a way that they interact to transform that A into another B. So we have a chemical reaction, A plus B goes to 2B. We also have diffusive processes where a high concentration of chemical A, for instance, at a particular location will diffuse out, eventually being evenly distributed all the way around the droplet. In a similar but not exactly the same kind of process is the equilibration of surface tension. So each one of the chemicals in our simulation has a surfactancy constant associated with it, which describes how it changes the local surface tension. And we have processes that cause material to flow in such a way as to equilibrate that surface tension. Finally, there are adsorption and desorption processes through which chemicals that are on the surface of this droplet can be released, so to speak, into the environment or absorbed from the environment into the surface. It's just transportation processes. The differential equations for describing all of these dynamics are in the conference abstract, but obviously I don't have time to go into them in any detail here. So each one of these oil droplets, most of the simulations we've done so far only have a single oil droplet in them. But they're situated in an environment which has chemicals which diffuse. They don't react in the environment, at least not yet. I haven't included that in the model at this stage. But recall that the molecules in the environment are adsorbed or desorbed in between the surface of the droplet and the environment. Finally, the motile oil droplets need some way of moving, and we do this in the way that we understand the motility to occur in the real world motile oil droplets, which is we track that the flow caused by the equilibration of surface tension, and we impart a force that's tangential to that flow that causes the droplet to move. So if you see, for instance, this black arrow at the top here, there's flow across the surface going this way, and flow also across the surface going this way, and these will combine to push the droplet to the right. So essentially we're taking our understanding of the natural phenomenon and including it in our model to cause these motile oil droplets to move around in simulation. An important feature, an essential feature really for this project is that the chemistry is not hardwired, but is something that can change easily from within the program, so that we can hand design chemistries, or so that down the road we can have artificial chemistries, open-ended chemistries, and so on, that allow for the creation of new molecules and new reaction as the simulation is progressing. So we have some simple programmatic ways for doing that at this stage, and all of this is done, all of the code is done so that this can all happen during a simulation. You don't need to sort of recompile it or anything like that or start over. So what did we do with this model? Well, the first thing that we did is we qualitatively recreated the experiment that I showed you a video of at the beginning of this presentation. We did that by creating 3 artificial chemicals that correspond to chemicals in the real world experiment. Perhaps it's easiest to start by explaining P. This is a fuel or precursor molecule. This is the molecule that's transformed into the surface tension decreasing amphiphilic molecule A. And that transformation only happens when pH is high. So we have H representing pH. When pH is high, then the precursor, the fuel, gets transformed, into amphiphilic molecule, into the surfactant, which causes the motion to happen. And lo and behold, we do see the motion. We can plot the concentration of these chemicals. These are the mean concentration of all of these reactants over time in the oil droplet. And then we can also look at the spatial distribution of chemicals over time as well. Of course, we want to go beyond what's already been done in the lab, and here we're taking baby steps towards that. We now, in this simulation, we have refuelable droplets. So in the original experiment, the droplet starts with some of this precursor, and once it uses that all up, it's done, it can't move anymore. But it's nice to work in simulation where it's easy to change things. And here I just quickly made it possible for the droplet to pick up fuel as it moves around. And I unfortunately can't get into the details of how this is happening right now. Feel free to ask me afterwards. But the droplet is moving from the high pH conditions back and forth between them and where it can resupply its fuel without any extra mechanism. It can sort of combine these two spatially separate resources and keep its motility mechanism going over time. So there's some cool stuff that we're doing, and that is continuing. I'm doing some experimenting with embedding, but with hand design of these kinds of reactions, so modifying the chemistry by hand, sort of designing what comes to my mind. And I'm also interested in using artificial chemistries, so open-ended artificial chemistries and random search of those artificial chemistries and selection processes and so on to try to see what kinds of smart droplets we're capable of finding. I want to do one, I think I just have another minute, so I can show you very quickly this simulation in action, running in real time. This is a sort of hand-designed chemistry. They got the droplet in the middle. The blue is a petri dish with some resource around the outside. And there's the gray Scott one-dimensional reaction diffusion chemistry on the surface of this droplet. And I can click, similar to Nathaniel's video, I can click and remove some resource, and this sort of destroys part of a mechanism or part of a self-sustaining pattern of chemistry on the surface of the droplet. And if I do this enough, then the droplet will start moving in a direction away from where it was perturbed. So it has some memory, in a sense. I might want to start arguing that it was damaged south, so to speak, and it's remembering to move up north. Or I can perturb it up here on the north side and damage it up there, and now it's starting to go south. I can damage it on the east side and so on. Or I can give it a really resource-rich environment. Oops, wrong button. And different chemicals can regrow around the surface, and it will eventually stabilize into a pattern where it's not going anywhere again if it's in resource-rich environment. So lots to be done, early days yet, but thanks very much for your time, and I'd love to take some questions.
All right. Woo! All right, we can take some questions if people want to raise their hand or just unmute themselves. Don't be shy.
I have one question.
Okay, great.
Hi, Takashi.
Hello.
Hi.
Hi, Matthew. My question is, as you may know, can you hear me?
Yes.
Yeah. As you may know, I did some computational simulation of this, and then the crucial point was including Navier-Stokes equations so that you can manipulate with how many numbers of convection flow, and then within the droplet, whether you can have a 2 vertices or 4 vertices, and that determines the motion directions and things like that. So I was wondering whether you think like a Reynolds number, for example, is one important issue for determining the directions and then also the fate of the droplet. But you didn't introduce this one in this thing, right?
No, that's right. Yeah.
But
So this
yeah.
model, oh, sorry, go ahead.
No, the second question is that we measured the pH gradient within the droplet, and then the gradient of the pH is opposite to the environmental pH gradient. So I thought that was the another reason why the droplet can move around. So if you can have any comments on this.
Sure, yeah. So to respond to your first question, this model was deliberately developed to be at a higher level of abstraction than the Navier-Stokes equation. So, you know, the computational cost of doing Navier-Stokes dynamics is high. And what I really wanted to be able to explore was different kinds of artificial chemistries, right? Different kinds of reaction networks that are going on the surface. So, and part of that's motivated by my understanding, which might be incorrect, that with the oil droplets in the chemistry, it's hard to have a great deal of qualitative diversity. Even as you say, you can have different number of vertices in the convection flow. It's hard to have a great deal of different types of oil droplets doing different types of things.
So Mate, what do you think of this Lee Cronin's keynote yesterday? I mean, this morning maybe. In Japan, it was last night. Yeah, that was, he said, using a new Darwinian evolutionary techniques in the lab, then he could, I think he automatically selected 5, 6, 7 different kinds of droplet movement, I think. And then we also found it manually. So I think it's, even though the same chemical compound and the environmental condition is the same, but still you're gonna have a different kinds of droplet movement.
Yeah, and I think that's really neat, but it is, as you say, it's sort of 5 or 6 different types of droplets, which is some qualitative diversity, and it's definitely worth exploring further. But part of what I wanted to explore is, well, you know, the combinatorics of chemistry and artificial chemistry is very high. So the potential for a great deal of variety there is interesting to me, and was part of the motivation of the model. Can you remind me very briefly what your second question was?
Well, the second question is the pH gradient within the droplet.
Yes. Yeah. So I don't have anything too specific on that, except to say that within this model, it is possible for the droplet to not only be affected by its environment, but to affect its environment as well. And I don't think I've looked at the precise issue of what you're saying about the pH gradient being inverted by the chemistry going on the surface of the droplet. But it wouldn't surprise me if I think that would be found in my model. I'd have to take a closer look.
Yeah, because I had a discussion with Martin that maybe this internal pH gradient is responsible for why the droplet can move around, can go away from the high pH, low pH, high pH regions and go to the low pH regions. That's why I was asking.
Right. And there's some really interesting stuff there about the idea of the droplet being able to continue motion even if the gradient were to disappear, right? If it's kind of constructing its own local gradient, then it might be able to persist moving in a certain direction, even if that gradient disappears for some period of time, right?
Yeah, right. But I was thinking that this is flow structures around droplet, but you do. So I wasn't quite sure whether this flow structure around the droplet, and that is responsible for the movement. And because of this convection flow inside the droplet, and especially when there's another droplet, the convection flow direction is aligned with each other like a Boyd model. So that motivated me to think that maybe there's a more strong interaction with the droplet when there is a I don't know, maybe the flow structure around the droplet. So it's not inside the droplet, but outside the droplet causes some perturbations in the flow structure that determines the interactions of the droplet. Yeah.
Right. So
anyway, thank you so much. It was a very good talk. Yeah.
Well, thanks very much. Thanks.
Lovely. Thank you so much. Let's give our speaker